this question, we will be learning thermal physics, especially focusing on the first law of thermodynamics. Let us take a look at this question. A fixed mass of an ideal gas absorbs 1000 joules of heat and expands under constant pressure of 20 kilopascal from a volume of 25 times 10 to the minus 3 meter cube to a volume of 50 times 10 to the minus 3 meter cube. What is the change in internal energy of the gas? Let us take a look at the PV diagram of this question. By PV diagram, I mean the pressure and volume diagram. Here is the PV diagram. You will notice that the vertical axis is the pressure axis measured in kilopascal, and the volume axis is the horizontal axis measured in meter cube. So whenever we draw the PV diagram, we will always draw the pressure axis as the vertical axis and the volume axis as the horizontal axis. Let's proceed to fill in the values in the PV diagram. Now V1 is 25 decimeter cube, whereas V2 is 50 decimeter cube. And from this PV diagram, we can see that there is an expansion of the gas as indicated by the question as well, from X to Y, indicated by the red arrow. So once this PV diagram is drawn, we need to understand certain terms in the question before we can proceed to solve it. The first thing that we need to ask ourselves is, what is internal energy? Now, internal energy is actually a sum of the kinetic and potential energy of the gas molecules in random motion. In other words, we are looking at the energy of the gas in a microscopic level, internally, not externally. That means all the forms of energy that's going on inside the gas is called the internal energy. Now, what is kinetic energy of the gas molecules in random motion? It is not just the traditional kinetic energy due to motion. In fact, there are other forms of energy that contributes to this kinetic energy of the gas molecules. Let's take a look. The kinetic energy of the gas actually has three forms of energy. The first one is the rotational energy of the gas, meaning the gas molecules can rotate about a certain axis. So this rotational energy contributes part of the Ke. Next, we talk about vibrational energy of the gas molecules. This vibrational energy is present because within the molecules, the atoms can vibrate, and this contributes another form of Ke. Last of all is the translational kinetic energy, which is the kinetic energy of the gas molecules moving about within the gas container. So these three energies added together will contribute the kinetic energy. What about potential energy? Potential energy also have three forms. Now the first form is the energy due to attraction between the gas molecules. The gas molecules themselves have protons and electrons. So between gas molecules, there are mutual attractions, sometimes repulsion, between the gas molecules. And this attraction or repulsion is a form of electrical energy that contributes part of the potential energy of the gas molecules. Next, within the gas molecules, there are chemical bonds. Chemical bonds contribute chemical energy, and this chemical energy forms part of the potential energy of the gas molecules. Last of all, we talk about the energy due to the mass of the gas molecules. In other words, we also mean the rest mass energy of the gas molecules, which is famously known as the E equal to mc squared. So these three forms of energy added together will give us the potential energy of the gas molecules. Next, Let's proceed to understand what is meant by an ideal gas. For an ideal gas, the potential energy is assumed to be zero, meaning we will treat that there is no attraction between the gas molecules, there's no chemical bonds within the gas molecules, and there's negligible mass for the gas molecules. So with all this assumption, then the potential energy of the gas molecules in random motion is taken to be zero. And with that, the kinetic energy of an ideal gas, U, is simply equal to the kinetic energy. So, with all these terms being explained, let's proceed to solve the question. Now, what's the equation we should use to solve this question? The equation we use comes from the first law of thermodynamics. And in equation form, it will look like this. The increase in internal energy of a system is equal to the heat supplied to the system plus the work done on the system. What is meant by a system? A system here means that it is a gas enclosed in a container. And a gas is characterized by its temperature, its volume, and pressure. So, these three characteristics will define the state of the gas. Now, let's proceed to look at the work done on the system. From our understanding of work done, we know that work done is force times displacement in the direction of the force. So the work done on the system, we will be looking at the force acting on the system. But this force acting on the system appears in the form of a pressure, because pressure is force over area. Because we're looking at gases, so it's not easy to just measure the force acting on the gas. Rather, we will measure the pressure acting on the gas. Now, when there's work done on the system, most likely the system should be compressed, meaning the gas is being compressed when there's pressure acting on it. So under this definition of work done on the system, a positive work done will mean a compression of the ideal gas. Conversely speaking, a negative work done will mean an expansion of the gas. Then how do we calculate work done on the system? Well, let's try to derive the work done on the system at constant pressure compression. So we know that work done is force times displacement d in the direction of the force. Now force, written in terms of pressure, will be pressure times the area times the displacement. Now if we lump area and displacement together, we'll have a change in volume, because area times length gives us volume. So we can calculate the work done on the system by using the pressure and the change in volume multiplied together. However, this formula only works at constant pressure and not at constant volume. Because if it's at constant volume, then there will be no work done. If the pressure is not constant, then we cannot use this formula P times dV. In fact, we have to use the method of integration, but this is not covered in our question here. So, in symbols, the change in internal energy of a system is represented by change in U, while the heat supply to the system is represented by Q, and the work done of the system is represented by W. Now, let's proceed to fill in the variables that we know. What are we needed to find? The change in internal energy. So change in U is what we need to find. Do we know Q? Yes. We know that the ideal gas absorbs 1000 joules of heat, as indicated here. Because it's absorption, so it is a heat supplied to the system. So Q will be 1000. What about the work done? Well, there's a change in volume, so we have to calculate that change in volume. So let's proceed using the first law of thermodynamics. This is the equation that we're using. And let's sub in the variables. Now, Q will be plus 1000 as mentioned earlier. And W, using the formula P times change in volume, where the pressure is 20 kilopascal, so 20 K, times the change in volume, so we take 50 minus 25 times 10 to the minus 3. Now you will notice that there is a negative sign in the question. Okay, there's a negative sign in the work done. Why? Because this is an expansion. For expansion, the work done is negative. So after putting all the necessary sign, let's calculate, and we notice that the work done on the system is a negative 500. So adding it with the heat supply to the system, the total change in internal energy of the gas is a positive 500 joules. Because it is a positive 500 plus, it will mean that it is an increase in the internal energy of the gas. The first law of thermodynamics is also another way to explain the principle of the conservation of energy. Now, you'll notice in the question that 1000 joules of heat is absorbed by the ideal gas. What happens to this 1000 joules of heat after it is absorbed? 500 joules of it goes to increase the internal energy of the gas, while the remaining 500 joules is used to expand the gas. So this 1000 joules is converted into two forms of energy. One form is internal energy, to increase the internal energy of the system, while the other 500 joules is to expand the gas, meaning work done by the system, to let the system do work. So there's no loss in energy or the energy is destroyed. I hope this example gives you a better understanding of the first law of thermodynamics. Thank you very much.